the graph to find a number delta such that. Well, in this particular case, they're not giving us these numbers, but they're very easy to determine, both of them, and then it's easy to make a decision exactly the way we made a decision before. So I know there is an x that I plug in to get 2.4. The function is the square root of x. There must be an x that I plug in to get 2.4. So in other words, I have the square root of x equals 2.4. How do I determine x?
Square y.
Yes. No, I have to square both sides. I have to square both sides of the equation. Awesome. So x equals, and when I think it's 576, so that's very simple to check. 2.4 squared, 5.76. So on that x coordinate, I have 4 here, and here I have 5.76. Now, there is another x value that I plug in the function to get 1.6. In other words, the square root of some x is 1.6. How do I determine x? Anyone?
We should do the same thing.
Of course. So x equals 1.6 squared. And I got 2.56. At this point, I have to determine this, a potential delta 1, and this, a potential delta 2. How much is delta 1 and how much is delta 2? Can anyone give us delta 1? Anyone?
Would that be 1.44?
Excellent. Can anyone give us delta 2?
$1.77,976.
Good. So I have to find the minimum of 1.44 and 1.76, which is, I know it's a silly question, which is 1.44. So that's the delta corresponding to epsilon equals 0.4, the smallest of the two. Any questions? So in other words, again, if there is a minor error in, of course, a symmetric interval, it has to be a minor error in the function, that will trigger a minor error or a tolerance. If there is a tolerance in the function, there's going to be a tolerance in x, and also vice versa. So if I have a minor error in the radius of a disk, so let's say this is the radius of the disk, it should be 4, but it's not 4, it's 4.1. Well, when I determine the area of the disk, which is pi r squared, I'm not going to get pi times 16. I'm going to get an error because there is an error in the radius. So that's basically the mechanism, going back and forth. If there is an error in the area of the disk, there must be an error in the radius of the disk, and vice versa. Okay, enough of this, unless you say, no, we want to look at another example. You can always say that now or next time, it's up to you. So tell me if you need another example or we move on. This is the only proof you will be asked to work on this semester. It will only be on a linear function, and it will always be the same what you just seen. So let me know we want to look at another example or we move on.
one other example, please.
Okay, would you like to choose another?
Mhm.
Okay, here it is. Here are examples. This is quadratic. We don't need to do that. I only need linear. Or you can make one up. It's up to you. If you want to make one up, just tell us a linear function, and x approaches something. Any function, any number, linear. Anyone would like to make one up? Tom, are you? Yes, go ahead.
X plus 2 as it approaches 5.
Good. So 5 plus 2 is 7. So remember, this is the function, this is the limit, and this is a. And we have to write a definition for every epsilon, in words or symbols. It's up to you. For every epsilon positive, I will find a delta positive such that every time I pick x close to 5, which means the absolute value of x minus 5 is less than delta. So this is a, x minus 5, delta. So x and a go with delta, and the function goes with the limit and epsilon. So this will imply that the absolute value of x plus 2 minus the limit is less than epsilon. And this is already done because the function you chose already has this. So from here we conclude that delta must be, which is very possible, delta must be what? Comparing these two, delta must be I have x minus 5 in absolute value. I have the less than or less than symbol. What can delta be?
Epsilon.
That's it. And number 2, show that delta equals epsilon works. Works by reversing the steps from above. Is this better? Is this okay? Anyone? Other questions? Okay, so we continue then with 2.5 continuity. Continuity. Well, this is a new concept. So first, let's see, what do I mean by continuity? So here it is. A few examples. And I need a fourth one. So here they are. Here's just one example. Notice what happened. I started the function and I did not raise the marker off the paper at any point in time. This is a continuous function. Here's a second example. Up. This is not a continuous function. This is called a jump discontinuity. Here's another one. I had to finish up here and go here and continue. This is not continuous. It's called infinite discontinuity. And there is one more. Also here, I had to do this, make this circle, up, circle, and continue. So this, the function is not continuous. It has a discontinuity. This is called removable. discontinuity. So what does that continuity at the point mean, if this is the point? Very simple. The limit from the left equals the limit from the right and equals the function value at that point. So we are combining now two concepts, the concept of the limit and the concept of the value, evaluating trend and evaluating together. If these three are equal, limit from the left, limit from the right, and the function value at that point, the function is continuous at that point. This is not. The limit from the left does not equal the limit from the right, but it's continuous from the left. Why? Because the limit from the left and the function value at that point are both equal. This one has a discontinuity called infinite discontinuity. It goes up and down. Even if it's like this, it's still an infinite discontinuity. Even if it's like this, it's still an infinite discontinuity. What about here? Well, the limit from the left equals the limit from the right, but does not equal the function value at that point. So let's write now the definition of continuity at the point. Very important. Definition of continuity at a point. As I mentioned, the limit from the left equals the limit from the right equals the function value at that point. This doesn't always happen, as we know. But if a function is continuous at a point, it must happen. The limit from the left equals the limit from the right equals the function value at that point. Now, continuity from, as we had it here, from the left. The left means the limit from the left of the function equals the function value, but it does not equal the limit from the right. So this is continuity from the left. A function can have continuity from the right. Then the limit from the right will be equal to the function value, but not to the limit from the left. So there are three types of discontinuities: jump, infinite, and removable. Now, a function is continuous again at a point if both limits and the function value are the same. It's continuous from one side if the limit from the right and the function value are equal, or the limit from the left and the function value are equal. Okay, so now we want to look at, and you can say, why is this so important, this extremely important for what follows in this chapter and later on? So this is section 2.5, and let's look at examples. Okay, so let's look at a graph first. They're asking us to, from the given graph, state the numbers at which f is discontinuous and explain why. For each of the numbers stated in part A, determine whether f is continuous from the right or from the left or none of the above. So at -4, what type of discontinuity does this function have at -4? So we're looking at problem 3 in 2.5. What type of discontinuity does it have at -4?
Would that be the remove one?
Awesome. Yes, it's removable. And the limits from the left and from the right are equal, but they're not equal to the function value at that point. Awesome. Yes, I should have mentioned that. Let me write that for you because I want you to have it in writing as well. I'll be right back there. So removable again. The limit from the left equals the limit from the right, but does not equal the function value. This is the condition for removable. So the limit from the left and from the right are the same, but they don't equal the function value at that point. That's removable. Awesome. Thank you. Great job. Okay, what about at -2? What type of discontinuity does the function have at -2? Jump. Very good. What about at 2? Of course, jump. What about at 4? It's slightly more difficult to say, but I would definitely consider this a vertical asymptote because it appears to be going to -infinity. So this is an infinite discontinuity. Is this function continuous here from the left or from the right? At -2.
From the left.
Yes, of course. What about at 2? From the left or from the right?
The right.
Of course. And what about at 4?
The right again.
Also from the right. Good. Okay. So the graphs are all the same thing. Explain why the function is discontinuous at the given number. What will you say? Why is this function not continuous at -2?
When you plug it in, it becomes 1/0.
Yes, it's undefined. Sure, the function cannot be continuous when it's not defined. Awesome. Okay. How will I show that the function has a removable discontinuity? I will have to determine the limit from the left and the limit from the right and just show that it does not equal the function value at that point. So would you like to choose one of these problems?
Oh, 26.
26. So let's take a look at 26. In 26, we have f of x equals x squared minus 7xn plus 12 divided by x minus 3. So show that f has a removable discontinuity at x equals 3 and then redefine f of 3 so that f is continuous at x equals 3. Okay? So let's take a look at that. Good. So it's very clear that x cannot equal 3. This is done, for sure. Because the denominator cannot be 0. And it will be 0 when x is 3. So the function is undefined. Now, let's try and see if we can factor the numerator. The denominator is already factored. And let's see what happens if we factor the numerator. Can anyone give us the factored form? Tom, are you back with us?
Minus 3x minus 4.
X minus 3, x minus 4. And here's what happens, and this is something very important. You would say, initially, oh, this function must have, don't write this. This function must have at x equals 3 a vertical asymptote. Not so fast. If the factor in the denominator disappears, this is not a vertical asymptote, but x equals 3 is a hole in the graph. If the factor in the denominator does not disappear, then it will be a vertical asymptote. But it appears that it goes away. The function is still undefined at x equals 3. You cannot change that. By simplifying it, it doesn't change the fact that the initial function is not defined at 3. So now the final simplified form is x minus 4, but this has to stay. And it's not a vertical asymptote because the factor was simplified. So this is just a simple hole. But a hole in the graph is the same with a removable discontinuity. Because the limit from the left of 3 is -1, and the limit from the right of 3 is -1. So limit as x approaches 3 from the left of x minus 4 equals the limit as x approaches 3 from the right of x minus 4, which in this case both of them are -1. But they are not equal to the function value of 3 because this does not exist. So this is a removable or a hole in the graph. Now they're asking us